which is dumb to me. Zero order will make sense. Good on this one? All right, there's an example in the book. I want to come back to this in a moment. I'll show you the example after we have a chance to look at a different order so we can see how orders are different from each other. So let's say we have a different reaction. This one winds up being a second order reaction. A yields B is second order in A. Don't get frustrated if you have no idea what order means. We haven't really learned it yet. We will. And the order is going to make a big difference as to how the reaction is going to proceed. But we're not there yet. If it's a second order reaction, that means that the differential rate law, which is right here, is rate equals some constant times the concentration, the initial concentration squared. That 2 up there tells what the order is. Really what that means is that the concentration of A has even more of an impact on the rate than it did when it was first order. Because yeah, you take whatever the concentration is and square it, and that dictates what the rate is. So the concentration affects the rate more the higher the order is. Now remember, that's equal to whatever the rate is. Rate is defined as the change in A over time. So we're going to take this part right here and set up another differential equation. Now let's see. I just wound up in the slide giving it to you. I want you to see how it happens though. So if you can humor me for one more integration, I won't do it again after this. Have you done calculus yet? Have you? Okay. All right, so here's what we have. We have negative dA. I'm going to turn that reaction, or not that reaction, the equation around. D concentration of A over dt equals K times concentration of A squared. I want the A's together. I should, I guess, have left it. No, that's okay. That's good. I'm going to bring the A term over here to be with the dA. So it's going to be 1 over negative 1 over A squared dA equals, I'm going to move that T over to the side with the K. If it's all right with you, if you have a pencil, hopefully, let's erase that negative sign and put it over there. Let's multiply both sides by negative 1 and get it over there. There. Now, integrate this over some time interval t. And it winds up doing this. What is the integral of 1 over A squared? What is it? No, it's not ln. Anybody?
Isn't it like ln of A squared?
No.
He just said it was.
We just decided that was not. Jonathan. Negative 1 over A. That's right. Yep, integral of this is negative 1 over A. You take whatever the power is, raise it by 1, but you have to change the sign because it's negative. Yep. Hadn't done that? It's cool. It's all right. So it's negative 1 over A at some time t minus negative 1 over A at time 0. That's the initial concentration right there. Equals, over integrating this side, it once again is just negative KT. And again, same way as before, this term right here is a constant because the initial concentration is what the initial concentration was. It doesn't change. The concentration changes, but what the initial was doesn't change. And that's what that number is, what the initial was. So I'm going to move that over to this side. And right now it's a negative, or it's minus a negative, so that really is a plus. So if I need to move it over, I've got to subtract it from both sides. So that means this. Use a different color. Negative 1 over negative kt minus 1 over a0. And it looks like I've got all negatives in all three terms. So I'm just going to multiply the whole thing through by -1 and make it like this. 1 over concentration of A equals, positive kt plus 1 over a0. This is very similar to what we wound up with last time. This term is changing as the time changes. It's like that's y and that's x. And then the k value is the rate constant is a constant, and the initial concentration is a constant. So once again, we have a straight line. And then we have a statement in red. Significant. If you have a plot of the inverse of the concentration versus time, if that gives you a straight line, that means the reaction is second order. So that's second order. I'd like to just show you what zero order looks like. If we have the reaction A yields B, and that means the rate is K times concentration A to the 0 power. What does that mean? What's the number to the 0 power?
1.
And physically, what would that mean? If the rate was dictated by a concentration to the 0 power, what does that mean? Wouldn't it mean really that the concentration of A, whatever it is not affecting the rate? It doesn't matter what your concentration is. The rate doesn't depend on it. It's not going to change. So yeah, that's what zero order means. It means that the concentration doesn't affect the rate. Now, I'm not going to do the integration on this one. This is what we would get, though, if we integrated this term equal to that, made it a differential equation. We get the A equals negative kt plus A0. No natural log, no inverse, it's just straight up A and A0. So that if you plot the concentration versus time and you get a straight line, just concentration versus time, that means that the reactant was zero order. I had skipped over one of these slides because that's okay. There's an example. We'll do it in a moment. I'm going to go back to it now. We good with the slide? Fantastic. On number 37, you don't have to write this down. We're not going to do the problem. I just want to talk about it. Here's number 37. There. The decomposition of hydrogen peroxide was studied, and the following data were obtained at a particular temperature. So this is the kind of problem you're going to have in this chapter. You're going to have experimental data, several points of experimental data. If I zoom out on the whole page, you see that the problems take up a lot of room because there's all these data tables that you have to work with. Your reaction was kind of funny to that just now. Anyway, but it's not bad. It doesn't make the problem harder because it takes up more room on the page. You just have to use it. These problems do take a little while, though. Gosh. We haven't gotten to the question. What's the question they're even asking? At the very bottom. Determine the rate law, the integrated rate law, and the value of the rate constant. That's the K value. Now, we haven't done, when it says rate law and it doesn't say which one, the implication is rate law means differential rate law. We haven't done that yet, so we wouldn't have to worry about that. However, the integrated rate law is something we're doing. So to find the integrated rate law, what we would do is we would take out graph paper and a pencil and a ruler maybe and plot all the concentrations versus time.
Wait,
Yes.
kidding.
If that were if that were to give you a straight line, that would mean that this is zero order, and you would just write the zero order reaction, not zero, the zero order equation, as you just wrote down. The last thing you wrote down was that zero order equation. Yeah.
Do we try all three like straight? I mean like if the zero order, let's say, doesn't work, do we go ahead and try the first order? And if it
Yes,
doesn't work,
that's exactly what I'm going to say. Yep. So try the zero order first because that requires the least work, just plotting that versus time. If that's not a straight line, if you get a curve, then take the natural log of these values versus time. I will tell you that the most common order is first order. So for a lot of these, the natural log versus time is going to give you a straight line. Now the slope of that line is the K value. Remember how it's natural log of A equals negative KT plus natural log of A0? That K is the slope. That's what the rate constant is. So you're kind of knocking off two of the parts here at once. But if the natural log versus time doesn't give you a straight line, then you go to these and you take the inverse of all these and plot them versus time. Yeah, I'm being serious. Can you have your calculator do this? Yeah. Can you take out a computer and have Excel do it for you? Sure. Or can you do it on paper? Yeah. Your choice.
Wait, really?
Yeah.
On the test, can we use our graphing calculator?
For the free response part, yeah.
Well, if you give us this on the multiple choice, we'd have to.
I'll give you some graph paper. Yes, Alan?
Do this stuff.
wait, hold on. Like, before the time, do we just ignore, while plotting, do we just ignore the plus or minus one?
Yeah, you can ignore that part right there. That just means they're close. That's good enough. Yep. So that's what we're trying to do with the integrated rate law is you're going to have this data, concentration versus time, and you're going to just plot. Start plotting until you get to one that gives you a straight line. And that tells you what the order is. So that's what we're up to. I'm going to just stop there and let you digest. We're just going to quit. Tomorrow, you saw what my slide was up there. We're going to go through all this and make a summary, and then we're going to practice lots. I do want to remind you that we have a reading quiz tomorrow. The reading quiz is an interesting one. Anybody go to the reading assignment? It's in the appendix of the book. It's not in Chapter 12. It talks about how to use a spectrometer and how it works. Spectrometer, and the reason we're doing that is because the lab on Monday is we're going to have these machines out, Spec 20s. If you've had GBBE already, some of you have, you may have a bad taste in your mouth about the Spec 20s because you use them. I hear a lot of people complaining like, oh no, not those, they never work. They work well with the labs that we do in here. We'll use them several times this year. So what a spectrometer does is it's a machine, instrument, that has a light bulb in it. You put a sample of a reaction into the path of the light bulb, and there's a sensor over here. Well, the reaction is going to absorb some of the light, and then the sensor is going to dictate or determine how much light it's absorbing, and then it's going to be able to give us some idea of how much concentration, based on the absorbance of light, the reaction has. So it works well. It's called Beer's Law, just like its sounds, beer. A guy named Beer came up with it. It's a pretty good college name. But there we have our reading assignment for tomorrow. So don't forget that thing. When you look at the assignment, say, what, appendix? But yeah, that's why we're doing that. It's just a couple pages there in the appendix. Right. All right, that's good.